Hello, everyone. I'm Ismail Khoffi, co-founder and CTO of Celestia. I'm going to talk a little bit about the architecture of Celestia, how it currently is, and give like a glimpse into the future. Whoop. They're not mine, yo. How do I fix this? Oh, okay. First, so on the agenda, I wanted to talk like two parts. Like the first part is I'm gonna recap the Celestia architecture, and in the second part, as I said, I'm gonna talk a little bit about like future directions. So it's not like a full-fledged roadmap, but what could be on the roadmap next year or so. Okay, so first of all, what is Celestia? I think most of you know, but for those who don't know, I'm gonna explain it from a high level, but also how it's implemented roughly. So Celestia is like the first modular blockchain network, and what it does is it decouples consensus from execution. So what does this mean? So in classical monolithic blockchains, usually how every chain works is a client verifies two things, right? It verifies that the header has consensus, and it also verifies that all the transactions are valid, right? Like it executes the transactions, makes sure the state transitions are valid. And then in Celestia, though, it only verifies if the transactions are available. It still validates that like the header has consensus, right? But it doesn't execute the transactions. It doesn't validate that what is posted on chain is actually valid. It just it just ensures that these messages that have been posted on chain are available, right? They are opaque blobs to Celestia. Like every application can post their blob onto Celestia, their message, and it's just ensured that these are ordered. There's consensus on the order, and then everyone can verify themselves that these transactions are available. So that's the main differentiator, and I'm gonna explain a little bit on how this works as well. You might ask, like, where does the execution happen? And the execution in Celestia happens in so-called rollups, right? Instead of this world computer model where like all the transactions are validated on like one chain, the state transitions are validated on a rollup. And you might ask, like, how does that work in practice? The light clients, for instance, they to validate that like a header is contains only valid state transitions. There's two approaches to this, which is like via fraud or validity proofs, right? Like in the Ethereum world, these fraud or validity proofs are posted on Ethereum, or they're settled on Ethereum. But like in Celestia, as there is no execution layer whatsoever on the main layer, these can be on like a different layer, like on a settlement layer, or they could be on the peer-to-peer layer. I just wanted to stretch this, as many people still perceive rollups as like enshrined with like with an enshrined settlement layer like on Ethereum. So now that we covered like how execution works, how the main chain works, I wanted to like mention the 4 guiding principles with which we designed Celestia, or like goals that we wanted to achieve. So it should be possible that a block is deemed valid only by checking block availability, right? Which means you can like verify a header as a light node without having to download the transactions, just by verifying the availability. The second principle is application message partitioning, which means every application only has to download their data, right? Like they don't have to download all the transaction data of all applications, only the transactions that are like necessary for their application. And then there's application message retrieval completeness, which is the same thing, but which means that they can verify that all the application messages, they downloaded all of them and nothing is missing. And there's also application state sovereignty, which means that all they need to care about is their state transitions and their, basically their state portion, and they don't have to execute other transactions of other applications unless there's a direct dependency. So next I want to talk about how is this achieved roughly. I don't want to go too much into detail, but there's mainly three key ingredients here in play. One is erasure coding of block data. Another one is a namespace Merkle tree and data availability sampling. So let's dive a little bit in. Erasure coding is a technique that is very well known, which is basically used in CDs, where you can recover data. So you add parity data, and you can recover data even if parts of the data are missing, right? So how this works in Celestia is the data is encoded in a certain way, arranged in a certain way. The original block data is split into equally sized chunks, and then you add this erasure coding in this square construction that is depicted here. The details do not matter. What matters is that you, this enables basically that you can, with a portion of the data, can always recover the whole data. So here we also commit, when validators create a block, they also commit to the erasure coded block and not to the original data only, as it is with other chains. And so every row or column here basically forms a Merkle tree, and these Merkle trees get committed to in a bigger overarching Merkle tree. And that Merkle tree is not a simple traditional Merkle tree. It is very similar though. The main difference is that a namespaced Merkle tree is used, which sorts the data according to their namespace. Each application can have their own namespace, and the data gets posted on Celestia, gets prefixed with a namespace, right? It gets sorted, and this is the data structure that ensures the property that I mentioned earlier. You can only download your portion of the data, your namespace, and you get a completeness guarantee of that as well. The third and most important ingredient that makes it possible for Celestia to ensure availability is data availability sampling, right? So as I mentioned before, the block is erasure coded, here depicted slightly differently, and then light nodes or nodes or clients can download only a small portion, 1% of the data, due to that erasure coding to guarantee almost 100% certainty that the data is available. Yeah, and so from a very high level perspective, this is how we built the system. We took Tendermint, right, and we modified, Comet BFT called today. So Comet BFT, previously Tendermint, we took that, modified it, and we added basically the data commitment that I mentioned earlier. We also used the namespace Merkle tree for that data. And the third component that I mentioned, the data availability sampling, is done in a different layer, in a different peer-to-peer network. We call the DA networks heavily reliant on BitSwap and libp2p. Huge shout out to the Node team that built this. No one has built this before. It's a huge effort. And yeah, that's a high level architecture overview. So, so let's go to the more interesting part, which is what are future directions for Celestia? How could a future roadmap look like? Or at least what could be some highlights here? So I mentioned this erasure coding, right? This is required for rollups to ensure safety, right? Like in the sense that you have to be sure that the data that has published has not been tampered with, like there's no validator that is like committing to garbage essentially, or something else, or some invalid data. So how do we ensure this currently? We have a fraud proof type that is called bad encoding fraud proof that every node can generate that like downloads either the whole block or even a row or like several rows are sufficient. They can like verify that the data matches the data root and can generate a fraud proof if that's not the case. That has the downside that theoretically lightnodes need to have to wait for such bad encoding fraud proofs to not happen to ensure like full finality of the block, right? An alternative approach is to use KZG commitments. I think if you saw Avail's talk yesterday, that's a technique they employ, which gets rid of the bad encoding fraud proofs. The question is, can we do better than this? I think we can. So with an alternative approach here is to use a ZK proof of the erasure, like to use a ZK proof that proves to you that the erasure coding and the construction of the data root was done correctly. So you can still compute quickly like the data root as before and send around the proof if necessary, if like you require finality, right? So that's a research direction. If anyone is into like ZK proofs, this is something you could look at. And I will later share a research forum link and the GitHub link. Another direction or another topic that we certainly will look at after launch is a trust minimized bridge, or like a two-way bridge from and to Celestia. So currently, if you wanted to use the base layer Celestia token on your rollup as a gas token, you have to use like other bridges and to use like other chains or third parties to get the token out and in to your rollup and back, right? Ideally, you would like the UX of this would be more seamlessly, such that developers can use the TIA token directly. So one naive way to do this, one way to achieve this, is you could enshrine like a general purpose execution environment onto Celestia that that acts as a bridge, right? That has the problem that it wouldn't be really neutral in the sense that you'd have to choose an execution environment, and also you'd basically reintroduce, yeah, like you would tamper with the original vision, which is like having only data availability and consensus. It turns out that you can do this without enshrining an execution environment. Mustafa came up with this idea where you basically leverage that ZK snark verification is more or less like looks very similar to cryptographic signature verification, right? You also have like a public key, and from that, like if you look at how ZK snarks work, it's like from the public key, it basically looks the same. So the user flow for how this would look like, roughly from a high level, is that a user would send a deposit of TIA to a verification key address. That's like a key address, like a public key on address owned by like a ZK program. So you deposit TIA to there, it gets like escrowed or burned, the transaction gets confirmed, and then the TIA would get credited on the rollup. And so you moved out you moved TIA into your rollup seamlessly. So this rollup will need to track the state of that verification key address. And yeah, so the more interesting part is like, how do you bridge back? You would send TIA, a withdrawal transaction of your TIA in the rollup, right? If the transaction gets confirmed by the state machine on the rollup, you generate a ZK proof. And that ZK proof like kinda simulates or acts like a signature on the verification key address on Celestia. So that would trigger the withdrawal of TIA. That's very high level. The devil is in the detail. There's a lot of like choices to make here. John would say a lot of implementation details. And indeed. Yeah, another hot topic is how to fix MEV, or rather how to apply current state-of-the-art MEV research and techniques to like the modular stack, right? There are several teams working on this. I think Skip and Flashbots are the most noteworthy here. The speciality, or like the difference here, is that MEV can trickle from the rollup into the base layer. Like the base layer validators could delay or like even censor batches from the rollups, right? So the question really is like, how do we apply solutions to MEV to this like more modular stack, especially given that there's like a very heterogeneous application layer? I think Evan's talk will cover this in greater detail. Don't miss it. It's like this afternoon. He will speak about how to break the proposal monopoly. Don't miss that talk. So this is like the long-term goal here that we want to achieve is 1 gigabyte blocks, 1 million rollups, and 1 billion lightnodes. So often when we mention this to people, it's like 1 gigabyte blocks, that sounds insane, right? And it kind of does, but we won't achieve this immediately anyways. It will be on demand. But we do believe that this is, like, as it becomes necessary, we will tackle this. And the question really is, like, how? I think we're very confident that we can go to, like, 100 or something very, very quickly. But to actually get, like, closer to that 1 gigabyte blocks goal, we will have to optimize Commit BFT's peer-to-peer layer, right? Like, the mempool is not made for super large blobs, and the consensus reactor, like the gossiping mechanism, is also not made for that. There's a lot of like low-hanging fruits and optimizations that we will do. One of them is already started, which is like the content addressable pool, cat pool. Callum implemented this already. Similar, the peer-to-peer, like the node peer-to-peer layer needs a lot of improvement to achieve this. Mainly block sync and dosing. Like, there's a lot of optimizations to be done, mostly very implementation specific. It might turn out that, like, in the future, in like several years, we have to merge the DA layer and the consensus layer again, like architecturally from a software perspective. And we might have to employ a technique called internal node sharding to achieve like the throughput on the consensus layer. Another topic that I want to stretch is we want like 1 billion light nodes. How do you achieve this, right? So we want all light nodes to run on all devices, like on all kind of devices. But I think the device we should target the next is the browser, because this is what like people are used to interact with in their wallets, and like they send transactions through like MetaMask and everything. What we want to achieve is running Celestia nodes, dosing light clients in the browser. So there's two approaches to this. One is having a different compile target for Celestia node Go implementation. Another one is having a Rust implementation. For the sake of time, I'm not going into detail, but if you want to hack on this, please talk to me. Yeah, there's plenty of other open problems and research directions. A few were already mentioned, for instance, by Yuma yesterday, the ZK quantum gravity bridge. Yeah, and I think one thing that last word that I want to mention is that we need to focus on developer usability. And if you want to do usability research for developers in the modular stack, please also reach out to me. Yeah, you can engage here with in our research forum and on GitHub. These are the main things. Thank you very much.